Hi everyone, this is James, lead developer at Stealth R&D LLC, which is a company that is dedicated to developing Stealth, which is a cryptocurrency that was launched in 2014. We developed the protocol, infrastructure, and whatever else the coin may need in order to ensure its livelihood and its vitality, utility. Stealth is was launched to be a cryptographically private cryptocurrency. It was one of the first cryptocurrencies to have Tor network integrated into it in a way that was very uh, forward thinking. It's recommended these days to actually, if you're going to run a cryptocurrency client, to run it behind Tor. We just decided just put it in. Why make it any harder when somebody starts up the client? It's got Tor. That to me, that just made a lot of sense, and people are finally, as of a couple of years ago or maybe a year ago, waking up to the importance of that. Um, so we believe that privacy is a key monetary property. Uh, it goes down to the utility of it in terms of its fungibility, and a non-private coin is not going to be fungible, and it's not going to be useful as a payment system. And the kind of the killer use case for cryptocurrencies is as a payment system. One thing that Stealth wants to work on these days is to improve the efficiency of the protocol. And towards that end, we developed what used to be known as quantum proof of stake. What I have here that my cursor is over is our website, stealth.org, listed in the marquee at the bottom. Used to be called quantum proof of stake. We've renamed it to Junaeth. We'll have to update the website. We're working on a new website, so I guess we haven't put the time into updating the old website. So it's going to read quantum proof of stake until the new website is up very soon. Quantum proof of stake, or as it is called now, Junaeth, is a scalable blockchain system that allows for 5-second blocks. Every 5 seconds, there's a block. So you only have to wait 5 seconds for a block confirmation, and the way it should work whenever it goes on mainnet. On testnet, it was this way. For block for transaction finality, which means it can't be reversed, which means if you pay money to somebody, that person can be confident that money will not be reversed. That only takes about a minute and a half or something like that. Let me just see if that number makes sense. Yes, about a minute and a half. So we're going to bring that number down. So it's a super fast 1.5 minutes versus Bitcoin, where there's no such thing as block as terms of transactional finality, and your confirmations are going to be 10 minutes on average, and typically, they can be longer, 40 minutes, an hour, sometimes 2 hours. Depending on the network, you might wait days. There were times when you could wait days for a Bitcoin transaction. So Junaeth, or as it was formerly known, quantum proof of stake, is in testnet. It's fully developed. I worked out all the bugs, and I've moved on. Not to say that I haven't continued to try to make small improvements to the protocol and refine it, but the basis of Junaeth protocol, 5-second block time, super efficient, is there and working, and it's a matter of improving, adding to the protocol. And a few things we will add would be feeless transactions, faster finality using a special type of Byzantine fault tolerant func method. But today, what I'm going to talk about is how we are also decided recently to put my efforts and the team's efforts towards working on an infrastructure. And one thing that along with privacy, one thing I really think is important for blockchain technology is efficiency. To have highly efficient systems that deliver information. I mean, that's what it really boils down to. All of computers is information. You look at a computer screen, it's just delivering information to you. You type into your computer, you're giving it information. So managing information needs to be highly efficient and for any kind of infrastructure. And so what I've done towards that is I've started to implement what we call the StealthExplore API. API means Application Programming Interface, and what that means is the client is running. You can type commands into it, or you can have a program that sends commands to the client, and it will send back blockchain information. So that's what I'm going to demonstrate tonight. Is I have basically the first working, not quite complete, but it's a working prototype of this API. And believe it or not, I've synced up the mainnet chain. So I actually this is in if you go to our GitHub, this is in the QPOS 3.0 branch. It's not on the master branch. You could actually build that branch. I might even try to bring it up here. QPOS 3.0. Yes. Let's see if this loads up. Yeah. So this is the branch. QPOS 3.0. 131 commits. I have a commit I'm going to do after this session tonight. I'm just going to clean up some code and put everything that I'm working on tonight. You can go build this and sync the main chain. You have to sync the main chain with the API enabled, which I guess I can show in a second. And you enable the API, and you can actually work with the API. Although right now, even though there's some complexity to the implementation, the actual API is still pretty simple right now. So all of the complexity to manage, what does it manage? What does this API manage? Basically, addresses and the money and the information about the money that flows into those addresses, flows in and out of those addresses. That's all really the sending functionality of a cryptocurrency is, but it's actually fairly complicated to track, especially in a blockchain like Stealth, which is originally, if you trace it back, is based on Bitcoin in terms of the concepts, using what's called a UTXO model, and it's not account-based, so that makes tracking the balance, say, of an address kind of computational. But here, what we're excited about is that all this is done real time and super fast, and the actual retrieval of the information is super fast, and the way that it actually organizes the information as it syncs the blockchain. I've synced the mainnet. I was doing it by Bootstrap at the same time indexing the address information, and that was syncing about just as fast as I would without all the address information. So it's really not a huge computational burden in order for the API to collate the information. And so let's see where I am here. Yeah, so if you go to inside this stealthcoin.conf file in the stealth data directory, you can put explore API equals 1. You have to do that before you start the client for the first time. At this point, it's still new. I will try to make it to where it can actually index the entire API very quickly without having to sync the blockchain. But we're early stage of development of the API right now. You put this command inside your .conf file for those of you who are familiar with configuring and running a client, and the API is enabled. You do have to build off the QPOS 3.0 branch that I just mentioned in that previous window. So what does this API do? I don't know if I answered that. I sort of addressed that. I don't know if I totally answered it, but every address, every time you send money in a blockchain, like Bitcoin or Stealth, Litecoin, many chains like this, you're sending to an address. And for example, in Bitcoin addresses, all of them start with a 1. Now with SegWit, they start with a 3. With Stealth, they start with an S. Um, and and you send money to that, and it's like you're writing it a check. And the way these addresses, the conceptual way to think about spending money is when somebody wants to spend this check you sent, they sign the check and they write a new check to where they're sending it. If there's change left over, they write a new check to themselves. So a single check in, that's called a UTXO, and unspent transaction output. It's a complicated name. When you sign that check, now it's spent, and you create 2 new UTXOs, potentially one sending where you want and one change back to yourself. So you get a check for 10 UTXO. You sign it. You got to pay this guy 9. You send 9 to that plus a fee. It's 0.99 back to you. You make a check for 0.99 to yourself. And those are 2 new UTXOs. That's a UTXO model. I've described it in many blog posts, but that's how it works. And that model is very useful. You need a model like that in order to have, say, full cryptographic privacy. But the problem with that model is it's difficult to, say, collate the address information. To get the balance of an address, typically, if you want to know the balance of address, you have to go to a block explorer. Okay, if you remember, this is the Explorer, the StealthExplore API. So it's kind of like having a block explorer right in your client. And people may think of this as a client abuse. Well, first of all, it's optional. You can put it in there. Second, if you implement it correctly, as I believe I have done, it's not a huge computational burden on the client. It can manage this information. Way more difficult for the client is to validate signatures. That's like what it spends all its time doing when it's validating blockchain, is validating the signatures. This other very collative type processing is very simple. So it's not a big burden. And SSD drives, internal memories, are huge, or gigabytes. The memory required, say you have 100,000 addresses. Well, each of those is 20 bytes. Okay, that's two megabytes. That's nothing. That's like nothing even on a USB drive. And then the balance is going to be in Bitcoin and Stealth are 8 bytes. So whatever that comes out to, nothing, 28. So we're talking about less than 3 megabytes for however many addresses I said that was, 100,000. So you have 100,000 and the addresses and the total number of bytes, just so the balance is very small. When you start talking about the other information associated with it, you're only really storing indexing information that says what that talks about how to reference transactions. And that's not a lot of memory either. So if you implement this correctly, it can be fast. You can deliver the information fast, and that's what I try to do. So there's a few commands to the StealthExplore API. Okay, so the first one, and one thing that I wanted to put in was a rich list. So wait, you're saying that the Stealth client has a rich list? I mean, come on, that's got to be client abuse. Well, it's not. A rich list is derivative, and it turns out um, it's derivative from what you really want. You want the address, money flow information. A rich list is a snapshot of that information where every address has a balance and they're sorted, okay, by balance. That's all it is. And if you use some computer science type principles, namely search trees, then you can get the computational complexity of managing and presenting a rich list down, okay? And the beautiful thing is search trees are not unique to my implementation. They're all over. They're in the C++ standard library. If you know where they are, you can use them and use that efficiency without a lot of implementation details required, or none really required of the actual search tree itself. You just have to know where in what uses it, how to use it, how to reference it, and how to iterate over a tree and things like that. That's all typical C++ stuff that you would know anyway, but you don't even know you're doing it. So I've tried to find every trick I could. And so here we have a rich list. Get rich list size is a command that says how many addresses are in the rich list, and addresses with a balance greater than dust. And dust is user defined. You could put it in the confirmation file, stealthcoin.conf, in the stealthcoin application data directory. And dust is 5 times the minimum fee. The minimum fee is 0.01 stealth. Dust is 0.05 stealth. And you can have it 0. So you could have you could manage a rich list for every single one, but I mean it's a rich list. Like if you only have 5 times the minimum fee, are you really rich? So, but it's good to know how the ranking is, the address distribution, and all that. If you really wanted to get a hardcore address distribution, look at it from some sort of statistical way, and you're really interested in that information, you could set your dust to 0, index the blockchain. Right now, in order to get this, to get the API enabled, you have to index the entire blockchain. That means you have to validate every single signature. That's going to change. We're in an early stage of development, and this is just how it is right now. Okay, and I totally recognize that it's unreasonable to have to validate the entire blockchain in order to index it for the Explorer API. But I haven't worked on that part yet. I've been working on the API, the information management, which is really the interesting problem here. And a rich list is an interesting problem because you don't sort by address, you sort by the balance of the address. So you either have to maintain a sorted list, or you have to calculate that. What I do is I choose to maintain the sorted list in the computer memory using a few tricks that I won't go into, but it's not as simple as you might think. You'd have to look at the code to see how I use in-memory memory management. Management's in the RAM, not on the hard drive, and use that in order to reference and manage the memory, the information that's going to get written to the hard drive. So that's the database is on the hard drive, and there's some in-memory management. And it all goes to getting a rich list and doing things like figuring out the rich list size very quickly. Excuse my voice, it's kind of cracking here from talking a lot. It's kind of dry here. So right now there's 2,195 addresses in the blockchain as of, I synced the blockchain with only 1.25 million blocks or so. Then I killed it to make this video tonight, and I'll try to keep syncing. I haven't really tested this out on this many blocks, but it certainly got that number pretty fast. What it did is it looked over the whole, there's an in-memory data structure that keeps kind of a digest of the rich list, and it goes over that in-memory structure and calculates this total number of addresses in the rich list. We can see how many blocks we're at here. 1,267,000. I believe it's adding blocks. Yeah, as we speak, it's synchronizing from the network. You're encouraged to synchronize from a bootstrap. I synchronized from bootstrap, had to kill it to make the video, started the client up, and now it's synchronizing from the network. And I don't know if you can hear a faint buzz on this video, but that's actually the fan on this little laptop syncing blocks. But in a day, it synced almost half the blockchain. And so it's pretty fast. I mean, it was less than a day. So this is an old laptop. This laptop is from about 2016. It's a Mac. It's an old MacBook Air. By now it's old. I still think of it as new, like we all think of our computers as new because they were expensive when we got them. But this is kind of the lowest end Mac that I could buy at the time for traveling. It was super light and stuff. Great machine. I still use it. Syncs a blockchain in a couple of days, 3 million blocks. Okay, so that's, let's see if it's added any more blocks. So the cool thing is it can, in that amount of time, it's added one more address that has greater than the dust on the rich list. So we can actually get, say, I'm going to do it like this. I'm just going to get the top 10. So there's this command, get rich, not get rich list size, just get rich list. And it's this gets the top 10. So you're probably thinking, oh, get numbers 1 to 10. That's not really how the command, how to think about the command. You start with, let's see, we start with this one, 10, and then it start with the 10th one and retrieve 10. So this will start with this guy here of 637034 SDVC as the first one that it lists, and then we'll have descending balances after that for a total of 10. So see, this top one here is SDCV with that balance, which didn't change over those few blocks. So it gets the top 10 and the second 10. The idea here is that if you have an Explorer and you want to present a page of the rich list, you can do 1 or 10 per page, and you don't have to download the whole rich list in one shot. This is planning for the future when there might be several million addresses in the rich list, and you might just want to get one page. So you do get rich list size, and say it was 21 million. Well, you'd want and somebody requested the 500th page of that. You could easily just get the 500th page and not have to download 21 million addresses. This is part of the stealth sort of paradigm for efficiency, where we kind of anticipate the usage when the blockchain scales up to global usage. It's not going to scale up to global usage if you don't design the blockchain and infrastructure for global usage. And I've been designing and working with blockchain for a while here, so I can actually think about these things in advance and program them in a way that I probably couldn't have a few years ago. So I'm planning ahead here. So there's 1 to 10. Let's see, it's 2194. So you can actually, you don't even have to know. You can get rich list. Start with 1 and give me a million of them if you got them. It's gonna bring out 2194 and that fast. It got all to 2,194 metadata. Most of that time spent was just putting together the printout. Actually reading, and it read each one of these from disk. It found each address, got the balance, read it from disk, and put it out the screen like that. And every block, if we look at how many blocks that it's downloading, and you can do what's called a hash, which will just digest the information it spits out into a number. And if this changes, like there's the hash of that. If it changes, hopefully it'll probably change. It changes every block. So all that information, these numbers and these addresses between those two amount of times change, and every time it updates a block, it updates that. So it's a super efficient way to collate this rich list. This is unlike most rich lists. You have to have an Explorer running. It's got a database. Well, Stealth doesn't use a typical like SQL database or anything like that. Um, I've I've done all of the data management for this database at the lowest levels that are practical, not the lowest levels that are convenient to program. But if I were to write at any lower level, I couldn't get any more efficiency out of it. I don't think. And so all of the management of that is about is as efficient as I could make it. And I'm using right now LevelDB, which is well, I don't want to say it wrong, but I think it's maintained by Google or something. And there's another one called RocksDB, but I think is maintained by Facebook. I can be corrected. This is just out of memory. LevelDB is good for on a on a hard drive. Typically, usually the old spinning platters, the big one, they have more storage capacity, but they're slower. RocksDB is optimized for RAM database or SSD, so super fast memory. So and the beautiful thing is I'm using LevelDB, and we can switch over to RocksDB pretty easily, and I'm going to do that, and it's not going to require a big commit. You're just going to use RocksDB. You're just going to build and install that dependency when you build the client, and the end user is only going to know that, and you won't even well, you have to resync the chain. You might have to, well, you'll have to re-index it, not resync it, but later. As of this moment, you have to resync it, but that's only because, like I mentioned, we're at the early stage of development. So yeah, I was playing with this a little earlier to pick out an address. So somewhere in here, yeah, is this address SHSZ31, typical stealth address. Typical looking, starts with a capital S. Some of them start with an R, like this one here, RY. They can start with RX too, and then a bunch of S's. This particular address is interesting because it has lots of transactions. Some of these addresses, may have large balances, but only one transaction. They're not that interesting, right? One transaction, it's great to have a big balance, but it's better to have a big balance with a bunch of transactions so you're interesting. So you can get all the information about this address. This address is not in the wallet of this client. This client, I minimized the number of keys in this client. It's only 2 addresses possible with this client without adding more keys, unless if you have a multi-signature address with those 2 keys. So you just this is just an arbitrary one. I could pick any one of these addresses here. I'm just going to scroll up all the way to the top where they get interesting. The really big ones tend to be more interesting than the small ones. S8 SEX. Why is that one interesting? I don't know. Okay. So we can do it with that one. Boom, and it spit out. Though it's interesting because of how many inputs and outputs it has. Ooh, this one's better than the other one. That's a pretty sexy address. So we can. The cool thing about that is it's got so many. You might think of it, as computationally difficult to get that information. It's not super highly efficient because I'm making use of things like search trees and stuff. It has 818 inputs and 1,511 outputs. The difference is the number of end spent. So each output is money going into an address, and each input is money going out of an address. And you're like, dude, why? Why didn't they do it the other way? Because addresses are on either side of the payment processor, which is the blockchain. So the blockchain processes payments. It's the important guy, not the addresses. So inputs are inputs into the payment processor, outputs are outputs to the other address. So that's from the payment process, from the blockchain sector. Input to the blockchain, output to the blockchain. So you send this address money, you have an input to the blockchain outputs it to who you're sending it to. From the perspective of the blockchain, which is really, the important thing here because it's the payment processor, the terms input and output make perfect sense. With respect to an address, it's like hard to, even if you just remind yourself of it, it's hard to get right. It's just so counterintuitive because you think of an account. Money goes into an account, out of an account. Well, an output is money coming into an address, and an input is money going out of an address. Bear with me, folks. I didn't invent this. Satoshi Nakamoto did. So I hope I just didn't repeat that. I remember I tried to make a different take of this and realized that I didn't have my camera on quite right. So if I just repeated myself, I did that sound exactly like I said earlier, but I think it was for the previous take where the camera wasn't right. So it has 1,500 outputs, which is money coming into the address. 818 of those have been spent, and the difference is 603 unspent. We can, and it tells you what the balance was and what the height was. So check it out. Let's see if the balance changed. Not really. So this person wasn't even staking, even though in this number of blocks here, a bunch of blocks, 1,000 blocks, less than 1,000 blocks, 800 blocks or something. The balance didn't change, but that's the balance as of 1.27 million. It's syncing from the network. I bootstrapped it. I probably mentioned this in this take already. I bootstrapped it to 1.25 million, and I've just been syncing in order to make the video. But you can actually, so a couple of things, there's a couple more commands to go over here. You're like, wait, what do you got, like 4 or 5 commands? Yeah, I mean, you can get stealth coin, you get address balance, and let's make sure that we got that. Yes. It's the same numbers here. That's another command, but you can get that command with the address info command. The address info command is helpful because say you want to list all the inputs or all the outputs or all the transactions. It tells you how many it is, so you can potentially retrieve just the ones you want, okay, and then just display those if you're writing a block explorer. If you're writing a wallet, you're going to need all of them in order to work with the address. You're going to especially need these guys, the unspent, so that you can calculate a balance and send it out. Right now, I don't have anything to access the unspent by themselves, but they do come out. Get address outputs. Okay, that's the command. It'll get all of the outputs, and you can tell it to start with 1. I'm going to do like 4. Okay, this one's got 1,511, and there's the last 4 output. 1, 2, 3, 4. Yes, good. Notice these are all spent. If you want to get just so say the last 4, you can see they're spent. So this one was this output was in this block. So this address, I'm sorry, got this money, which was nearly that looks basically sent from Bitrex, the 0.02 fee, probably. This address got it, was sent themselves 1,000, had to pay a fee to the exchange of 0.02, and that happened in this block, and it was this transaction ID, and this was the output of that transaction ID. If you know the output number, the output index, as they say it, or V out is whenever you port it to the API. So that one was spent. This one was spent, but let's see. So let's just get address info again. And we'll get the last, nothing's probably changed on this, but we might as well just bring it up. Well, we can just come here, get outputs, and we can get the last 3. So it has outputs 1, so we want 1, 1, 5, so what the last 3 is 0, 9. And just give me 3 of them. So there's the last 3. And notice how these are not spent. So the newest ones are not spent. Makes sense. It spent the old ones, the newest ones are not spent yet. Uh, the spent ones are all going to be in the input list. But the input list is going to tell you what transaction and block that it was spent in. And it will, you can match that up to the output list and calculate a balance and stuff, which we probably won't get to in this video. So, but what if we just want to get all of these? Let's go to 1. So that's just a big number, way bigger. It takes a second to put all that together. Yeah, so it was so this is, so even with this one, most of the time was spent building this JSON actually to report. So it took a second to put together however many, 1, 2, 3, 4, 5, 6, 7 times 1511, lines. It had to, most of that was calculating, most of that time I can tell you was calculating the block hash, retrieving the blocks and all that information. But if somebody synced the chain, that would be about as fast as it would. That would be a lot faster from an Explorer to like collate that many transactions and put it up there. And this can be done faster when an output is made. All of this information can be written, but it's not. It's calculated. So looks like I can improve the efficiency there. So the last command is not simply get outputs. So let's just go. So now it has 818 input. We can just check out the inputs. So we'll do this. We'll just get the first 3. Get address inputs. Yeah, 1 to 3. It only had to calculate 3 block hashes, and yeah, that's where it's spending all its time, retrieving the block and going. It's got to go to the disk, retrieve the block, and then calculate the block hash from it. So I think I can make that a lot more efficient. I'll make that a lot more efficient because that was quite a bit of delay to retrieve those. But that was like a couple of seconds. That's unacceptable. I'll make it faster. I'll figure out how to do that efficiently. That's why we have these tests. This is the first time I've tested it with nearly half the blockchain. So you're looking at real-time testing. So there's the first 3. These just say what transaction was it spent, what was the previous transaction ID, and what was the out. So these will be, you can cross-reference these to that list of outputs I just had, and then you can see how much they sent on this one. Which is not in here because all the outputs, they have how much was sent right here. That's the amount. So these work together, and you can get a full picture of all the activity of any address in the blockchain, even ones with thousands of transactions. If you're running a light wallet, it's unlikely that a single address is going to have thousands of transactions. The whole wallet might have thousands of transactions, but definitely 1151, that needs to come back in a split second. I'm going to figure out where it's taking time. I'm sure it's calculating block hash, looking the blocks up. Does it really need to go to the disk drive to look up the blocks? Probably not. There are in-memory data structures that are already part of the protocol from Bitcoin that will have this information. So I'm going to pull it from those. I just didn't realize it was, I didn't really think about it when I did it. This is why you test, so you can see these things. Okay, so yeah, that's all of it. I showed you how everything works. Hopefully I've convinced you this fast. This is the first, I first tested this yesterday. all the code looks to be working pretty well. Now I'm going to go back and you'll see the development process. So that it's unacceptable how fast that 1151 took 2 seconds. That's probably faster than any block explorer could do that kind of thing. But this is stealth. We don't mess around, and we'll make that faster. We'll definitely make that faster. This is going to be and so now you can see utility. Somebody who's designing something, they want to work with the blockchain. They don't want to run a client. They don't want to run a block explorer at the same time. They just want to just run one piece of software that's got a direct pipe to the blockchain information. And this is the way to do it. It standardizes the API because it's part of the reference client, and it doesn't get any more standard in blockchain than the reference client, the Stealth client, and it's all coded in there, and so everybody knows what the standard is that works with this, and so somebody could have some service where they provide the API with API keys. So a few things we're gonna do is we're gonna implement the bit. It's called a Bitcoin Improvement Protocol 32, which is hierarchical deterministic wallets, where you can give it a particular key. It can derive all the keys related to that key, related to a wallet that provides that key. This is how Trezor works, and then give all the information for every address in the blockchain and spit that back out for that key. So somebody can write a light wallet, say in Python or in JavaScript or some new language that's cool, like Go or something, and literally in a few days, like as a hobby, and you get a light wallet, and because all you had to do was fire up the client, enable the API, index the blockchain, maybe from a snapshot if you really wanted to get up to speed fast, or just run the bootstrap, which will take a couple of days, and then they would have the full API, and they would absolutely know how to work with it. It wouldn't be some third party that had an explorer that had to set the explorer and the client and all this. It would all be right there for them, and standardized and well documented. But this is their first look. This is my first look. We both had a look at it today. I think it's pretty cool. I tested these yesterday, but not on 1.25 million blocks, and I think it works pretty darn good. It works better than anything I've seen, but I'm going to make it work better. But with that, I'm going to go ahead and sign off. I hope everybody has a nice weekend, and yeah, I'll see you next time when I have some new cool stuff to show.